Hi everyone. In this video, we are going to prove the explicit formulas that I gave for the different, if you recall, in terms of some coefficients in some factor of the minimal polynomial of a generator of f over e. We'll repeat the statement and some related results that give a more explicit understanding of how the different exponent behaves in terms of fairly simple valuation that one should compute. Ideally, this should have been part of the physical lecture, but we won't have time to prove everything there. And still, I think it's good to see those particular proofs. They kind of summarize things we did and kind of connect the abstract and the more computational aspect of AG codes. Okay, so this is the unit we're talking about. And just as a reminder, recall that if f over L is a function field extension of E over K, and you take a small prime divisor in the smaller function field, then a basis of f over E, just function field extensions, no function, just field extensions, for which the following holds, namely for which every integral element over P in F can be written as a linear combination of these zi's, your basis, but the coefficients are not coming just from E, but rather just from OP. So if that happens, if this basis has this property with respect to little p, then we say that this is a local integral basis or an integral basis of O prime P over OP. Right, and you should think of it, the quantitative are different. So actually, they are as written here. Sorry, you are given little p, and then you ask whether I have a nice basis for p. And by nice here, we mean this thing. Okay, and as a reminder, recall that if zi's is a local integral basis, then of course all of them are in O prime p, right? Because given this, you can just choose the coefficient ones for z1 and 0 for the other ones. To see that z1 is in O prime p, and same for z2 and so forth. But knowing that, namely knowing that z1 up to zn are integral over p, it doesn't mean you have this equality. It only means that the right-hand side is a subset of the left-hand side, right? So any OP combination of the zi's, which are OP prime elements, well, this is certainly an OP prime, but it doesn't necessarily mean, usually it's not, sometimes it's not the case, that every element which is integral can be written like that, okay? Okay, and the next thing we saw was the complementary module, which is, all functions in F, such that if you multiply them by any element in the integral closure of OP, and trace it down to E, you will actually land in OP rather than just in E. Yes, so this was a kind of a slightly weird definition, and we later understood the complementary module better, but that's what we did. And the claim that we didn't prove, it's not so hard, but some things worth proving and some things are somewhat less proving, and that's the example of the second case. So if you have a local integral basis of f over E for P, namely you have this equality rather than just this kind of inclusion, then the complementary module is spanned by linear combinations with scalars coming from OP if you take the dual basis for the zi's, right? So z1 star up to zn star, this is the dual basis for z1 up to zn, right? Which was defined using trace and so forth. So in that sense, when this is as large as possible, always it holds that this is a subset of that, and that's a subset of that. That's part of the, what led to this claim and so forth, which we skipped. But what I'm saying is that, once this is tight, then this is tight also, right? Once OP prime, once this is large enough to express all of OP prime, then this is small enough to express exactly the complementary module. Okay. Okay, and we finished, I think, with that lemma, the statement of this lemma, which tells you that if you have a finite, say, degree n, separable extension of function fields, and y generates f from E. So, I mean, you know that there's always such a y using the primitive element theorem, but let's say you have a y like that. Actually, in our settings, you are going to generate f using E and a y, right? So for example, in our settings, you have like maybe fq of x, and then you're going to extend it to fq of x and y such that, right? Say y squared is x cubed minus x. So what you are doing actually is, defining the function field using one more element, which is algebraically dependent on previous elements, right? So that's our starting point usually. But from the primitive element theorem, whether or not it was your starting point, it doesn't matter. There is always such a y. Anyhow, so let's say that phi is the minimal polynomial of y over E, right? It's a degree n polynomial. And y is definitely a root of that polynomial. So you can factor the minimal polynomial. You have t minus y, and then you have some other polynomial of degree n minus 1, where all the coefficients are in f. Right? Because, I mean, phi itself is over E, but these are not necessarily in E, of course, but definitely they are all in f. This is because phi is a polynomial over E, in particular over f, and t minus y is a polynomial over f. And when you divide two polynomials, then the resulting polynomial is in the field in which both of them are defined. So this is in E and this is in f, but they're both in f. So this polynomial is in f, namely all the coefficients are in f. Then what this lemma tells you is that you can actually express the dual basis, which was somewhat abstract, in terms of those CIs and y. So it turns out that the dual basis, and recall the sequence is important, the order is important, the ith element there is C sub I over phi prime of y. Okay, so it's, I don't know, maybe unexpected a little bit, but turns out that these coefficients are really important, and also phi prime of y. Note, by the way, that phi prime of y is not 0, because, phi, the extension is separable, so y is separable. So the minimal polynomial of y has no repeated roots. In particular, y is not a repeated root of the polynomial, which is to say that phi prime of y is not 0. So it makes sense to divide by phi prime of y. That's what's written here. Okay, so let's turn to prove this lemma, which again, I think it's kind of a remarkable lemma. It tells you that, all the abstractions, at the end of the day, once you fix kind of a generator, a basis, so to speak, it's quite explicit. The only thing you need to do is to, find the minimal polynomial. In our case, for example, y squared is x squared minus x. It gives you immediately the minimal polynomial. You need to, compute a derivative, which is like formal derivative, which is very easy. And you do need to divide that polynomial by t minus y to get the CIs, but these are just like computational problems, which are very simple, not like something too difficult. So I think it's nice to see this abstraction like takes form of something that's like feasible to do. Okay, so let's prove the lemma. So what we want to prove is that these guys form a dual basis for these guys, right? So that these are the dual basis of that. So we need to take something from here times something from here, trace it, and see that you get 0 or 1, depending on not whether they correspond to the same like index or not. So what we want to show is that for every I in L, if you take the ith element from the, what we claim is the dual basis, times y to the L, this is the ith element, this is the Lth element. When you trace it, you should get 0 or 1 according to whether I equals to L or not. Right, so this is the delta IL. It means that this is 1 or 0 depending on whether or not I equals to L or not. Okay, so how would you do that? So first of all, let's consider the n distinct embeddings. Let's denote them by sigma 1 up to sigma n of f over E into some algebraic closure. Right, this is a separable extension, so you have n distinct embeddings because the minimal degree of y is of degree n. And let's denote by yj the element in which sigma j sends y to. Okay? So what do we know? We know that by Galois theory, these are precisely the E conjugates of y. Namely, these are exactly the roots of the polynomial phi t. So you can write phi t, you can factor it in some, algebraic closure or something. You can factor it like that. Right? So yj for every j between 1 and n is a root of this polynomial. Maybe sigma 1 is the identity, so you have t minus y, and then you have the rest. Right? So when you take the product of t minus y, j is not 1, you get exactly that, right? But I'm factoring it because now I'm in some large enough field, maybe the algebraic closure, whereas this is the polynomial written in f, so it may not necessarily factor. It also, could potentially be irreducible or reducible. It depends over f. But anyhow, we have this, and if we are going to differentiate with respect to t and substitute y nu for some fixed nu, then what I claim we get is this thing. Right? Because if you differentiate that, right, you have a sum. How do you differentiate product? You have a sum of products where in each product you have one element, one term missing. Right? Everything here is like monic. And so you have a sum of n of those. In each of them, one of the yj's will be left out. And once you evaluate that sum of products at y nu, then the only surviving summand is the one in which y nu is not present. Right? So that's exactly this thing. So the only summand, there was a full sum here, but now the only summand that's left is this thing. So it was t minus yi when I is not new, and then you plugged y new there. So that's the derivative of phi prime at y new. And now I want to consider, it looks kind of comes out of nowhere, but for every L between 0 and N minus 1, so the L's are, I think of it as the power of y's. Okay? I want to define this polynomial, phi sub L of t. So it's a polynomial which I want to show it at the end of the day is the zero polynomial, but I'm currently defining it like that. It's this thing minus t to the L. So what is this? So here you have, you run over all j's. So yj, we are going to y over yj, and we have this thing. So I have phi of t over t minus yj. That's phi of t is divisible by t minus yj because yj is a root of this polynomial, but I don't know where the coefficients of this thing lie. I'm just writing it as something in f bar. It's, the algebraic closure, so that's fine of f. And I multiply that by this expression. So this is yj to the L divided by the derivative here, evaluated at yj. It may not necessarily be clear why I'm looking at this right now, but let's look at this polynomial. Again, my goal is to show that this polynomial, for every fixed L, I have a different polynomial. I want to show that for each and every L like that, this is the zero polynomial. So then therefore I get, that these two are the same polynomial. Like this very complicated polynomial at the end of the day to t to the L. And from there, the proof will essentially follow. But let's first prove that this is the zero polynomial. So let's see. So note, because of the previous calculation, that for every nu between 1 and n, if you are going to evaluate this phi sub L, L is fixed. Phi sub L at y nu, what would you get? So because of the previous calculation, right, we know that the derivative is this thing. The derivative of phi y nu is this thing. So, okay, so use it actually in a second. So first of all, this thing, this part, phi of divided by t minus yj, when you sum over all j's, for a similar reason to before, this thing is precisely t minus the y's that are not j's. T minus yi for y not equal to j. The only summand that will survive is the one in which j equals to nu. Right? Because when j equals to nu, then this t minus yj cancels it out. Okay, and in the rest of the for the rest of the j's, you have a t minus y nu sitting here, and when you substitute y nu to t, you get 0. So the only surviving j here is that corresponding to nu, and for that particular j, this thing is exactly this product when you evaluate it at y nu, right? Because you'll have t minus yi for I not equal to j, but j is nu, and then instead of t, you just plug in y nu. Okay, so you'll have that. That's the only surviving term, and with the corresponding part here, which is y nu to the L divided by phi prime of phi nu. I just plug j equals nu because that's the corresponding term there, summand. And by the previous calculation that we did, this and that are the same. So they cancels out, right? So phi prime of y nu is this product, which appears here. So this is just like 1, and therefore this gets cancelled with that, and you get 0. So to summarize, for every nu between 1 and n, y nu is a root of phi sub L. These are n distinct roots because the y nu's are distinct because this is a separable extension, right? So all of the roots of the minimal polynomial are distinct, and the degree of that polynomial on the other end is at most n minus 1, right? Because the degree of t to the L is at most n minus 1 because L is at most n minus 1, and the degree is here, well, this is constant in t, and this is a degree n polynomial divided by one of its roots, so it's a degree n minus 1 polynomial. Everything here is a degree n minus 1 polynomial, and we sum them up. So this means that phi L sub t is actually the 0 polynomial, right? Because it has too many roots otherwise. And as I said, this implies that actually this weird expression is precisely t to the L for every L. Okay. So I just recapped that here. And so what I'm doing here is I'm just going to apply a sigma j. So these two lines are kind of maybe a bit too nitpicking. What I'm saying here is that now every embedding of sigma I of f to f bar, it extends naturally to some function from the polynomials in t over f to polynomials in t of f bar by simply applying the sigma I to the coefficients without touching t. Sigma I of t is just t. Don't worry about that. So what I'm saying here is that for every j, if I'm going to, no, sorry. So looking at this thing, so we know that t to the L is that, but in that expression, every time you see a yj, if you remember, this is just sigma j of y. So you have a sigma j of y here, here, and here, and sigma j is of course multiplicative and additive, so you can kind of pull it outside, and instead of writing sigma j's applied to the yj's, you can write just the sum, apply it to the sigma j of this expression, right? Because on the other direction, sigma j of this thing is sigma j of that times sigma j of that, and then the sigma j goes below the power of L, and even with inside this polynomial, right? Because it just respects addition and multiplication, so you can kind of pull back the sigma j all the way such that it acts on this function. And okay, so now let's get back to our CIs. Recall that phi t minus y, phi t divided, sorry, by t minus y is this thing, where the CIs appear. So I just wrote here those CIs. I know that, sum from 0 to n minus 1, and that I left at is. And now what I'm doing is, as I'm switching the order of summations, so I'm summing over i's and then over j's. Yeah, and the t to the I is here. And if you look at it for a second, this is precisely, what you're doing here. You sum over all embeddings of something, which is precisely the trace of f over a. Right? The trace is the sum of all embeddings. So this is, you sum over I. T to the I has a coefficient which is this trace. So this is here. And then if you look at it for a second, you'll see you can compare coefficients. Here you have polynomials in t, here you have polynomials in t, a very simple polynomial. So you can see that here the only polynomial surviving coefficient is that of t to the L with coefficient 1. And so this means that this is 1 when I equals to L and 0 otherwise, which is precisely what we wanted to show. Okay, with this we can move on and talk about a bound on the different exponent in terms of valuations. So we have the following theorem. Same setting as before, f over L is a finite separable function field extension of U over K. F is generated by this Y. And I'm assuming here that Y is integral over OP. I'm not assuming yet in this theorem that Y is like that 1Y, Y squared, and so forth is an integral basis for OP prime. I'm just saying that Y is defined, at all primes above little p, namely Y is in OP prime. It's an integral closure of OP. And as before, let phi be the minimal polynomial of Y over E. And my claim is that using this polynomial, you can easily bound the different exponent of every prime divisor above little p. And the way the bound works is you're just going to evaluate at the particular prime divisor above p that you care about at phi prime applied to Y. So you should think of this as very abstract, like the left-hand side, and you should think of the right-hand side as very tangible, something that you can compute quite easily. So that's a remarkable result. And the remarkable thing is that this is actually an equality if Y is an integral, if 1Y, Y squared, and so forth is an integral basis over OP. That's the next theorem. But let's start with that. I mean, the next theorem builds also not just on that theorem, but also on its proof. So let's look at the proof of that theorem first. But even without equality, I mean, usually what you want to do is to bound the different exponent from above, because that participates in Hurwitz's genus formula, and you want usually to bound the genus from above in order to get, at least in the coding theory context, you want to bound the genus growth. So that's the right direction, even if all you know is that Y is in OP prime. Okay, so let's see. The proof starts by, again, factoring phi of t as to t minus y and this remaining part. And recall that phi is a polynomial over OP, right? Because that's kind of our assumption. The assumption was that phi is in OPT. If I recall correctly, it follows from the fact that y is in O prime p, right? Recall that, it's not if I recall correctly, it's true. Recall that to say that y is integral over OP means that the minimal polynomial, its coefficients are in OP. Right, so like integrality means that there is a polynomial for which the harmonic polynomial that vanishes at y, for which the coefficients are coming from the base ring, OP in our case, but we proved at some point that the minimal polynomial will always witness that. So you don't have to look for another polynomial. You can, but you don't have to. The minimal polynomial will have this property that its coefficients are coming from the base field, the base ring. Yeah, so anyhow, the fact that we know this means that phi of t is over OP. Now that's not to say that the CIs are in OP. They are. They are related to that. We'll see in a second, but all we can say for now is that CIs are in F, right? Because generally speaking, that's the one easy thing that you can say about it. Because again, y is in F, and this is a polynomial over F. So when you divide polynomials over F, you get a polynomial over F. However, what I'm claiming is that the CIs are not in OP, but they are in this ring, this subring of F, OP of Y. So the way to see that is kind of backwards induction. So for example, Cn minus 1, that's why I say backwards, because you start from the biggest one. Cn minus 1 is just 1, because this is a monic polynomial, and the coefficient of t to the n here is 1, and the coefficient of t to the n here is obtained once you take this times that. And that's the only way to get t to the n. So c to the n, Cn minus 1 is 1, which is certainly an OPY. What about Cn minus 2? well, let's look at the coefficient of Tn minus 2. So how would you get a Tn minus 2? You can either take, this and y. No, sorry. I'm looking at the coefficient of Tn minus 1. So I'm looking at this times t, right? So this contributes to Tn minus 1, Cn minus 2, and then y or minus y times Cn minus 1, t to the n minus 1 will give you another contribution. It's like a little convolution there. And the contribution of that summand to the coefficient is minus y Cn minus 1, minus y Cn minus 1. So anyhow, you got that this thing is in OP, right? Because the coefficients of phi are in OP. And Cn minus 1 in this case is actually 1. So you got that Cn minus 2 minus y is in OP, which means that Cn minus 2 is in y plus OP. Just move it to the other side. So it's y plus like a constant in my mind, a function in OP. But it's just in particular something in some polynomial in y with coefficients in OP. A very simple one, but and you can do that. You can continue this one. So using that, like looking at that, you can see that the coefficients of t to the n minus 2 will then be Cn minus 3 minus y Cn minus 2, kind of analog to that. That's in OP because the coefficients of phi are in OP. And by induction, or just because we did it a second ago, that Cn minus 2 is in OPy. So this means that Cn minus 3 is in OPy because it's a y times something which is in OPy and so forth. So generally speaking, you'll have Cn minus I minus Tn minus I plus 1 in OP, and from there you can infer about this being in OP. Why? Good. So what I just said is that all of those CIs are in OPy. And a similar proof can be used to show that the powers of y's, are linear combinations of CJs with coefficients in OP. It's the same thing, right? So, sorry, I moved ahead. So here you looked at it and try to, locate, like put the CI somewhere. But if you want, you can see from here that the y's are linear combination of the c's, right? So for example, here, instead of writing it like that, you write that, well, y is in OP minus or something like that, plus Cn minus 2. And then from here you'll get that, again, you'll focus on the y, right? And you'll do the same backward induction, and you'll see that the yi's are actually linear combinations of OP with coefficients coming from CJ, or linear combination of CJ with coefficient coming from OP. That's the better way of thinking about it. Okay, so we have this in mind. We are going to use it in a second, but let's try to see what we are trying to prove. So what we want to prove is that the different exponent satisfies that. So the different exponent of capital Pi over P is bounded by this valuation. And another way of saying that, equivalent way of saying that, if you just recall yourself the definition of the different exponent in terms of the complementary module, is to say that for every element in the complementary module, the capital Pi valuation of Z is at least minus the capital Pi valuation of this thing. Right, because an element, so Z is in the complementary module, if this is larger than the minus of the different exponent, right? So, and there is an element which gets like equalities. So there is an element which gets equalities all the time. That's the TP that we said here. So, so this is the same as that. It's just an equivalence. Okay, so let's go ahead and prove that. Right, so I just recalled it here. So what we want to prove is that for every Pi above little p, and for every Z in the complementary module of little p, you have this inequality. Now, by the lemma that we proved before, we know that this thing is, well, lemma 3 tells us more, but lemma 3 tells you that this is the dual basis. Right. It tells you that this sequence is the dual basis of y, 1, y squared, and so forth. Too much, yeah. So by lemma 3, we know that this is a basis, first of all, of f over e. It's, even the dual basis of some basis. And so you can certainly write z, regardless of the fact that it's in the complementary model. Just because it's an element in f, you can expand it according to this basis. And the expansion will take, the scalars from e, potentially. But now, because z is in the complementary module, and y to the L, I mean, we know that y is integral over p, so certainly y to the L is integral over p. So we have that, if you look at this trace, right, so YL coming from OP, and Z is coming from CP, and the complementary module has this property, like that's the definition, that when you trace an element from the complementary module with an element from OP prime, you'll get something in OP. So on one hand, you know that. And on the other hand, you can just kind of expand Z according to that and switch, like take the sum outside of the trace, and also the RIs. You kind of slide them through the trace because the RIs are in E, and this is a trace of F over E, just identity on E. And so you get that this expression is just this sum. Now this sum, you have this expression here for every I. You trace this, multiplied by that, and these are precisely the elements from the corresponding basis and its dual. So this is going to be 1 precisely when I is L and 0 otherwise. So it means that the only surviving summand out of these, so the only surviving I is when I equals to L, and there you get a 1 here, which gives you the RL. So this tells us that the RIs in this expansion, because the Z is in the complementary module, is not just from E, it's in fact from OP. Okay, so Z is actually, you only use OP scalars in order to span an element in the complementary module. So that's what I wrote here. And now, by the above observation, so first of all, if you can, so what you can do is you can take this 1 over phi prime y and take it outside, and then you will be left with this sum of products of Ri, Ci, but we know that the Ri's are in OP, and the Ci's are in OPY. That's the folding backwards thing that we did before. So the whole sum here, except for this, which I took outside, is in OPY. And OPY, because y is integral over OP, certainly this is a subring of this integral closure. So you get this inclusion. So what's written here? Well, Z, it can always be written as an element, as this times an element in OP prime. Put differently, or not put differently, if you apply any PI valuation to Z, then the PI valuation of an element here is always at least, it's non-negative, right? Because the valuation of PI is some ramification index, times the valuation of little p of that function. And this is non-negative, of course, and ramification index are non-negative. So the valuation of PI at Z, of Z at PI is at least the valuation of this function according to PI, which you can also write as minus the valuation of PI at this thing without the inverse. And if you recall, that's exactly what you wanted to prove. That for every Z in the complementary module, and for every I, you have this inequality. Right, that's what was here. Right, for every I and for every ZP, you have that, because then that tells you that these are precisely the values for the different exponent, or not precisely, it's just an inequality, but it tells you that the different exponent are at most these valuations. Okay, so with that, let me proceed to the theorem that has some equality into it. It's actually quite short given what we did. So again, same setting, f over L is a finite separable function field extension of E over K, and f is generated by y over E, and again, y is integral over OP, phi is the minimal polynomial of y over E, and let's say, as before, that the capital Pi's are the prime divisors of f lying above little p, then what I'm claiming is that, well, in the inequalities that we had before becomes equalities when, and actually if and only if, 1, y squared, and so forth is an integral basis of f over E with respect to p. So I wrote it like that here. So what I'm saying here is that, and I explain it, OP prime is the same thing as this ring, the subring, usually the subring of it when y is in O prime p. And I claim this is the same thing as saying local integral basis. Indeed, if y is in OP prime, this is our assumption all the time here, then of course, this is a subring of that. But when y squared y to the n minus 1 is a local integral basis, then by definition, it means that every element here can be spanned by these things with coefficients of OP, which is precisely this ring. Okay, so this is a shorthand saying that it's the same thing, but a more compressed notation for saying that y1, y squared, and so forth is an integral basis of OP. Okay, so let's prove that. In some sense, you only care about one direction. You care about the direction which this one, because you really usually what you want to do is to compute the different exponents. And so this tells you that under this condition, you know what the different exponents are. But it's also nice to see why it's equivalent. So then why when the differences are all aligned as they should, then that is a local integral basis. I don't think we use that to prove local integral basis. Our basis is a local integral basis, but it's just, let's just do everything. Okay, but let me first recap something that we had from the previous proof. So if you recall, we proved that in the previous theorem. Namely, we proved that the CI's are in OPY, and the YI's are in, in this thing. They are a linear combination of the CI's with coefficient in OP, and I'm going to take that with us. And now for the fourth direction, and I think the direction is the one that I'm interested in. Yes, so we assume that OP y is O prime p. Again, this means that 1 y squared is a local integral basis of OP prime. When by the previous result we had, this is lemma 2 and lemma 3, I'll remind you. So maybe let's go to lemma 2. Lemma 2 tells us, it's claim actually, yeah. Claim 2 tells us that if you know that you chose a basis, like a local integral basis, and you have equality here, then the complementary module is precisely this ring with the zi stars as the dual basis. And lemma 3 told us what are the zi stars when the basis that we care about is 1 y squared, and so forth. And that's lemma 3 here. So going back to the proof. So lemma 2 and lemma 3 tells us that this thing, right? The complementary module is there is an equality, not an inclusion like that. Yeah, it equals precisely to, you can write it as the local integral basis, as a linear combination of the local integral basis. The fact that this is the local integral basis is lemma 3 times element times scalars for OP. And so from that we know that CP, well, I just kind of taken this thing outside. So CP, every element in CP, or CP is equal to this thing. Now the OPCI, as I said here, you can replace the CI's with the y to the i's, which is just another way of saying OPY here, right? That's the same thing. And now using our assumption, in this direction, we can replace this OPY with the integral closure of OP. Right, so we just proved that under this assumption, the complementary model is precisely this thing. So this is the TP that we cared about. Okay. Right, so again, under this assumption, we prove that, and therefore, by definition, the different exponent is precisely the valuation of this thing. Right, because generally speaking, the different exponent was defined, if you had a TP here, not with a 1 minus, then the different exponent was minus the valuation of TP. So, the 1 over cancels, take care of the minus here. Now, in the other direction, which again is less useful, but slightly more interesting in terms of a proof, you want to prove that if this holds, namely if the different exponent is always equal, namely for every I, to the corresponding pi valuation of the derivative of phi applied to y, then indeed 1y squared is a local integral basis, assuming all the time that y is integral over OP, of course. And as before, the non-trivial inclusion is this direction. Right? It's always the case that this is a subset of that, assuming that y, as we always assume, is integral over OP. The interesting question is why everything integral over OP can be written like that. So the way to do so is, just take an element here. Let's take a z in OP prime. And first of all, just being an element in F, and since 1, y squared, and so forth is a basis of F over E, you can write z like that. You just expand it using this basis. And now, by the observation we made, we know that all the CJs are in OPY, that was from before, which is always in O prime P. And I'm going to collect 3 things. So orthogonal to that, I'm just saying that the CJs are also in OP prime. In a second, I'm going to take Z times CJ. And Z is in OP prime, CJ is in OP prime, so Z times CJ is in OP prime. And just recall that this is our assumption. Right? I'm assuming that the complementary model is this thing. Right? This is the... it follows from our assumption. This assumption translates to the fact that the complementary model is precisely 1 over phi prime I. This is the corresponding TP, right? Because we said that the complementary model, in order to figure out what's the TP such that CP is TP times O prime P, you only need to know the valuations. So if you know all the valuations are correct, namely phi prime Y has the right valuations, or actually 1 over phi prime Y has the right valuations, then it will also generate, in this sense, CP out of O prime P. So this is something that we know. And therefore, what I claim is that the trace of this TP times CJZ is in OP. Right, because CJZ is in OP prime. That's what we just said here. The product is in OP prime also. And 1 over phi prime Y is in CP. Right, you can just take a 1 here. And an element in CP times an element in OP prime, when you trace it, you get something in OP. So all I just said is that this trace is in OP. But now let's open Z. So right, I put a dot here, just because I wanted to make sure that we understand this is in OP prime, and this is in CP, in order to get this equality, this inclusion. But now I actually want to kind of split it differently. So I want to look at, okay, this is element in OP, but I want to write it as a trace of this times Z, because I want to expand Z. So Z, recall, was just, I just expanded it according to the basis 1, y squared, and so forth. So I wrote it here. This is Z, right? And then I can pull out the sum and also the TIs, because the TIs are in E, recall. The coefficients of the expansion of Z according to this basis is, of course, in E. So you can pull it outside, and then you'll be left with this trace. Again, basis, dual basis. So the only surviving I j is fixed. So the only surviving I is when I equals to j, and then you are left with tj. Namely, tj is in OP, right? Because this whole thing is in OP, but this whole thing is just tj. So tj is in OP, and so z, which was defined like that, with the only knowledge of this coming from E, but now actually from OP, is actually in OPY, which is precisely what we wanted to prove, because we took a general element in OP prime and we proved that it's in OP of Y. Good, so, oh, sorry. So that was the proof. Let me just tell you one or maybe just one more corollary that I'm not sure we are going to use, but just, to see some other instantiation of this kind of nice philosophy of, abstract becomes more tangible. So again, under the same assumption, we have a finite separable extension of function fields, and f is generated by this y, and y is in OP prime for some p that you care about, and its minimal polynomial is phi. So now assume that you know that for every capital P over little p, the valuation of the derivative actually is 0. Which another way of saying that is that this is a unit in O capital P. So you just need to come up with like some way of inverting it to verify that. It's actually even easier than computing valuations, right? You're just deciding whether the valuation is 0 or not. Then what this tells you, so this is a simple test, and what it tells you is that P is unramified in the extension, and also that this is a local integral basis, like two things. So this is a way of checking that, y1, y squared, and so forth is a local integral basis, and also it kind of rules out ramification. Actually, the proof is kind of a one-liner, so let's just do it. So by the previous theorem, not previous theorem, just the bound theorem, we know that, well, the different exponent is always non-negative, but in the previous theorem 4, we proved that this is bounded by the p valuation of the derivative, and now our assumption is that this is 0. So this means that you have equality to 0, so both of them are equal and are equal to 0. And therefore, by theorem 5, which told you that, if you have equalities all the time, then that's if and only if this is a local integral basis. Good, so now theorem 5 is used in the kind of unorthodox direction in order to prove a local integral basis. Some basis is local integral. And also because of the di's are 0, all the d's are 0, or any particular d is 0, then we know that by Dedekind, regardless of characteristics, we know that this means that the ramification is 1. Right? This was a corollary after the Dedekind sphere. Good. So using this, you can actually more easily figure out whether a basis is local integral, and kind of make sure a place prime divisor doesn't ramify. There is another one here which will be useful when we are going to very shortly talk about Artin-Schreier extensions. Maybe I'll just let you view it, and I'm probably not going to prove it. Maybe I'm going to state it in the physical lecture. Okay, hopefully this was helpful.